right, we're now recording. Let me get on the current slide. And, oh, why is the computer? Ah, there it goes. Now it's caught up. The electrons were a little slow. They had a long 4th of July weekend. All right, I don't know of any major announcements going on now. So nothing to do there, I don't think. Any questions on anything we've covered so far? All right. Well, we left off last time in Chapter 3, Applications of Differentiation, Newton's method. We talked about Newton's method, but we didn't get to do Newton's method. So I know it was a long time ago and a lot of barbecue since then, but hopefully y'all remember what it is. It says calculate 3 iterations of Newton's method to approximate the 0 of f of x equal x squared minus 2, yep, and use x sub 1 equal 1 as the initial guess. Okay? So, how would we proceed? What would be a good first step? Say again? Yeah, very good. Take a derivative. Let me get my pen set up. Would be a good first step. Okay. All right. So f prime of x is equal to what? 2x. Okay. Now, with that in mind, they've given us an x1, so we're going to start with x2. And what would x2 equal? If you need to go back, well, let's see. Go back a slide. Here's what Newton's method is. X to the n plus 1 is equal to x to the n. This will be 2, 1, minus f of n, f of x of n, divided by f prime of x of n. Okay? So that will be x sub 1, which we have, minus f of x sub 1 over f prime of x sub 1. Okay? So what would that be? X sub 1 is is 1 minus, and then what is f of 1? Say again? Yeah. Negative 1 over, and what's f prime of 1? 2. It is, okay? So this would be a minus minus is plus. It would be 1 plus 1/2. That would be 1.5. Okay? Agreed? So there's our first iteration. Get Patrice here. Patience here, I'm sorry. All right. So let's move on to x sub 3. And what would that be? Okay, please don't make me write all that down again. That would be 1.5 minus 1.5 squared what next? F of 1.5 minus 2 over over 2 times 1.5, which would be 3. You see, over f prime. Okay? Got it? This is Newton's method. We're on in Chapter 3, Application of Differentiation, 3.8, Newton's method, on page 230. This is example 1. Okay? So let's, goodness gracious, how this gets messed up. Okay, so this will be 1.5 minus, and 1.5 squared I believe is 2.25, isn't it? Minus 2 divided by 3, so that would be 1.5 minus 0.25 divided by 3. Now some of you have a calculator, while I'm marking Malcolm here. Figure out what that is. 1.5 minus 0.25 divided by 3. Anybody? Got to periodically keep an eye on my computer. It's fading in and out, so I don't think I've got a good connection, but it's connected right now, but I've got to keep an eye on it. 0.083. Oh no. 1.5 minus 0.25 divided by 3. Yeah, 1.5 minus 0.25 divided by 3. I think what you gave me was 0.25 divided by 3, maybe. Yeah. 1.41. Okay. Now, is that as many digits as you got?
There's a 7 after.
Huh?
There's a 7 after.
Okay. 7, is that all? Or more?
No, it stops there.
Is that it?
Yeah, that stops there.
At 7. Okay. All right. Let's hang on to that for now. Okay. In fact, don't clear that. You just cleared it from your screen, didn't you? Okay. Okay. So let's do x sub 4. Okay. It says do 3 iterations. This will be our third one. Okay. So it's 1.417. So don't erase that from your screen. Minus, in fact, put it in memory if you can. Okay. Minus, recall that squared, 1.417 squared minus 2 over 2 times 1.417, which would be 2.834. We're doing Newton's method. This is page 230, chapter 3, application of differentiation, 3.8 Newton's method. First example with it. Anyone got it done yet? At 1.41432? 22. Does that keep repeating, or is that as many? Okay. Is that as many digits as you have on your calculator? Okay. So we got 1.4122. Does anyone know what the real answer is? What is the 0 for that one? F of x equal x squared minus 2? You do, you just don't realize it. Set that equals 0, right? That's what the 0 is, right? And then add 2 to both sides, x squared equal 2, x equal the square root of 2. So will someone punch in the square root of 2 and see what the answer is? Four, 2, one more digit. 1. Look at that. Look at that. The myriads. No, that's not what we're looking at. Okay. All right. Bottom part of the alphabet's coming in strong now. The top part is rather scattered. Middle is missing. Okay. So in just 3 iterations, we are now within 1, 2, 3, 4, 5, 6 decimal places of the actual answer. And as far as I know, no one's come up with a faster method than good old Isaac Newton did back when he first developed calculus. He developed this way to find the zeros of an equation. Pretty amazing. And it gets there and gets there really rapid. Any questions? And frankly, that's close enough for government work for me, okay? They all won't condense quite that quickly, but they do. The book carried one more digit there, and they actually had it to, that was a 1/6. Your calculator rounded it to a 2. So if you look, I'm sorry, I said 6 and wrote 2. Oh, but then my eraser didn't pick up. Okay. And let's see if they give what the square root of 2 is. 1.414214. So, because of your calculator round off, this actually got closer than what that indicated, because this is 1, 2, 3, 4, 5, 6, within 2 of the 7th digit. That is pretty good, okay, for a method to approximate a 0, okay? Within 2 millionths of the actual root. Wow. So let's take a look at how they did it. They'll do a table and everything else. Any questions before we move on? So let me clear what I've done. Let's see what they do. Because f of x is equal to x squared minus 2. You have f prime of x. The first thing you do, take the derivative, equal 2x. The iterative formula is x to the n plus 1. It's equal to x to the n minus f of x to the n divided by f prime of x to the n. And so that would be x of n minus x of n squared minus 2. That's your f of n divided by 2 times x of n. That's your first derivative. Okay? Plugging in the numbers then, and they don't show you the operations, they just do it and tell you the results. If you plug in the 1, they told you to use that as your first guess. F of n was minus 1, which you got. F prime was 2, and f sub n divided by this divided by that is minus 0.5, and 1 minus 0.5 is 1.50, blah, blah, blah. Plugging that in to your x sub n, f of x sub n was 0.25, which you got, divided by f prime, which is 3, which you got, and that ratio, as Tarika was telling us, was 0.08333333, and when you do the division, subtraction there, to more digits than we had, it's 1.41666666, it goes on forever. Leaving that on your calculator, plug that into x sub n, and minus plug that in here, which would be that number squared minus 2 divided by 2 times that number, and that gives you, that division gives you this, subtracted from this gives you 1.414216. And you could go on, but after a while, I'll just tell you this, if you go too many times, you start getting ridiculous answers. You're like, wait, why? Well, you've exceeded the precision that your calculator can do. And so when they're doing the subtraction, and anytime you have a subtraction, and you're getting up into very, very small numbers, numbers that are very, very close to each other, they can be subtracting off, and since these digits out here aren't significant, they're round off, your you're propagating a round-off error. So stop after a while, you know, especially if the answers start going a little wacko on you, because you're actually exceeded the precision of your calculator. Yours only had so many digits. This one went one more digit than that. After a while, you would get digits that don't make any sense. So what the calculator does for you, when you ask it to find the zeros, it gets it within the tolerance of the calculator, and when you get within that, they stop. And they don't do anymore because they know they're going to give you false readings after that. So that's pretty close. Okay? Of course, in this case, you know that the two zeros of the function are plus or minus root 2. We went for the positive root 2. To 6 decimal places, that's 1.414214 as opposed to 216 that we got. So that's after only 3 iterations of Newton's method, you have attained an approximation within 2 millionths of the actual root. That is pretty close. Okay? And here's the first iteration, as they show here. You started with this one, came down, found what alpha 1 was. That was your minus 1. The slope was 2. So you did the this, and then you found the x-intercept here. That gave you 1.5. Then you go up to 1.5, do the slope there, and that gets you even closer. And in no time, you can't even see the difference between your answer and your dot there. It's really, really quick. Okay. If you had chosen an x equal minus 1, you'd have gotten to the negative of that just as easily. Okay. Any questions? All right. They skipped example 2, so let's go back and pick up example 2. We'll do that here. And by the way, if any of you have can access the website, larsoncalculus.com, you can go there for an interactive version of this type of example. Use Newton's method to approximate the zeros of f of x is equal to 2x cubed plus x squared minus x plus 1. Now, just looking at that, I know I can't factor by grouping. That's the only technique I have in my belt to factor a 4-term polynomial. That won't work. We could try other techniques and methods. We do know by Descartes' rule of signs that you have 1, 2, or 0 positive real roots. That doesn't help us a lot. And if you did the f of minus x, this would change sign, and that would change sign. So you'd have a minus here, plus, plus, plus. So that would give you just one negative real root. So we'll know we have one negative real root. Frankly, I would go for that one first, but I don't know if that's what the book's going to tell us to. Says continue the iteration until 2 successive approximations differ by less than 1/10,000ths. Okay? And they said sketch a graph, and when you do sketch the graph, and they show it in the book, you see there's only that one root, and it's the negative root. That's why I said not because I knew that, but because I knew there would be at least one negative root, I would begin there. And it looks like to me that negative 1 would be a good place to start. So let's let x sub 1 equal negative 1. Okay? Now, what else do we need to do? Take a derivative. F prime of x is equal to 6x squared, second, plus 2x minus 1. My screen is fluttering like crazy, but so far the power stayed on, so I guess we're okay. All right, so our x sub 2 is going to be what? Minus 1 minus, now we need to plug in a minus 1 for, let's write it down, f of minus 1 over f prime of minus 1. So it'll be minus 1 minus, lots of minus signs here. Okay, what happens if we plug in negative 1 to your function? What does that give you? Negative 1 cubed is? Negative 1 times 2 is? Negative 2 plus a negative 1 squared is 1. So negative 2 plus 1 is negative 1. Minus a minus 1, which would be plus 1. That gives you the 0. So this gives you a 1 there, right? Divided by 6 times negative 1 squared is 1. So that's 6 minus 2 minus 1. So that's a minus 3. I mean, 6 minus 3 is equal to 3. Okay? So this gives you minus 4/3. I'm not going to write it as a decimal number, but got it, right? Okay? Our x sub 3, and by the way, how much do these differ? These differ by 0.333. Okay? Nowhere close to 0.001. So we want it within plus or minus 0.0001. So that one's out. Okay? Let's try again. Negative 4/3. Now, if you got it on your calculator, leave it whatever that is. In fact, store it would be good. Minus, and then we're going to do 4/3 cubed. And I don't want to do that. I want y'all to punch it in your calculator, okay? Whatever that is. It'll be a negative 4/3 cubed times 2 plus 4/3 squared plus 4/3 plus 1. Anyone got it yet? It's negative 2 times 4/3 cubed plus 4/3 squared plus 4/3 plus 1. It's going to be a positive, no, not necessarily. What will it be? Anyone got it? Now the negative part is negative 2 times 4/3. What you got?
Negative 0.6296.
Okay. Probably a round off. Okay. Divided by 6 times 4/3 squared minus 8/3 minus 1. on the bottom. -9. That's it? Wow. Nice. Okay. So you got 3 minuses here, so that turns out being a minus. So -4/3 minus that. 0.6296, blah, 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 blah. Okay. And then here's Ashley, right? Yeah. Oh, and by the way, I forgot to tell y'all earlier, I do have your second test graded. I can't return them yet because I don't have them all in. But if you want to see your scores, you certainly can do that. So come see me after class or during break or something. I'll let you see your test scores. Everybody so far has done quite well. Anyone got that calculated yet? Anybody? Help me, help me. Anyone got it?
-1.26.
-1.367.
No, 26.
267. Okay. Second?
It's 26337.
Okay, wait. Okay. -1 point.
26.
26. 33. 7. All right. And before it was -1.111. I mean 333. So now we're within 0.07 approximately. Still not close enough. What's that? I don't know. He did it for me. It was. Okay. It's 6 times 4/3 squared, which would be, right? Well, when you square it, you lose it. Okay, 6 times 4/3 squared minus 8/3 minus 1. What do you get? Something different? And Evan's here. Bottom part of the alphabet, really strong. Top part, pretty loose. Middle part, missing. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. Got it. Okay, so we're still not quite there yet. Did you get that 9 or something different? Second? 7? Yeah. I don't have a calculator, so I can't check. Let's see what the book got. I can do that. Oh, well, they started at a different place, didn't they? They started at 1.2, -1.2. So they would have something quite different. But if we keep going, we should still get there. Okay? We're not super far off now, but we have some ways to go. So let's do our x of 4. Because guess what? Even if you mess up a little bit, as long as you're in the ballpark, it's still going to zoom in on it. So this will be a -1.26337 minus, 2 times, and by the way, we're on Chapter 3, Application of Differentiation, 3.8, Newton's Method, page 230, bottom of the page, example 2. 2 times a -1.26337 cubed plus a -1.26337 squared minus a -1.26337 plus 1. That's your numerator. Divide that by your denominator of 6 times a negative 1.26337 squared plus 2 times a negative 1.26337 minus 1. Okay. Someone with a calculator, please do that. It's great if you can store this number. If you store it as soon as you get it, you get all the digits in there too. You don't have to type them all in. Then you recall here, the minus is already in there. Minus 2 times recall cubed plus recall squared minus recall plus 1. Divided by 6 times recall squared plus 2 recall times recall minus 1. If you, at least the old calculators had recall that way. I don't know what the new ones have. They should have something very, very similar. Anyone got an answer yet? Actually, some of the newer calculators, you can actually put the function in and the derivative of the function in. And you can just do recall minus function recall divided by derivative function recall. You know, I mean, it's function 2, recall function 2 or whatever. So, or function 2 evaluated at recall. What you get now? Anybody? A real pain if you have to type all those digits in there every time. You risk missing a minus sign or something else. Anybody? Got an answer yet? Does calculators slow you down, don't they? I'm just kidding. Anybody? Hoping it starts off with a negative 1.2 something. Someone tell me something.
Negative 1.233.
Wait. Negative 1.2 what? 23? 33. 1.233? 86. Okay. Now, how did that differ from before? 0.03. So, it's closer. Then you get the idea. I don't think we have to carry it on forever. But you just keep doing it. It's only going to take a step or more before you're going to be close enough to your tolerance. I just don't have enough room to write it all down. But if you plug that one in, it'll get you even closer. And after a while, you're going to be within 0.0001. Convinced of that? It works. They used a different starting point, so I can't go by the book. Well, actually, they got 1.23375 as their next iteration, And that's certainly so much closer. You're almost 0.0001. You're 0.00011. So not quite within that. 2 more steps and you'd have been there for certain. Maybe just 1. So anyway, that's how it works. Now, let me go back a slide to the last one where we had the figure of it. Oh, it's actually forward a slide. Well, no, this isn't a good one. Okay. I wish I had the picture in the book. Okay. But on this slide, if you had chosen 0 to be your first estimate, you'd never get there, because the derivative of the function at 0 is 0. And guess what? You can't divide by 0, and Newton's method says x of 1 or x of n minus f of n divided by f prime of n. So if you happen to pick the place where it's 0, it's going to blow up on you. It will not work. Okay? Now, I want to look at this one as well. Here's going to be the picture for this one. I'm going to erase this. Is that okay? Okay. Here's a picture of this one. If you pick anything from negative infinity up to, it looks like about negative 1.6 or 7 or something like that, you're going to zoom in on it. It may take a while if you get way too far off. But if you pick anything past this 0 here, okay, I mean this maximum here, or anything down here, you're never going to get there, because you see you have that loop to overcome, and it's not going to do it. It's going to take you this way, and you're going to be forever over here stuck in Never Never Land. You have to be close enough so that you are going to, it's going to point you back towards the root, okay? And that's what the next phase is talking about, okay? Here, when, as in examples 1 and 2, the approximations approach a limit, the sequence of approximations, x1, x2, x3, up to xn, keep going, is said to converge. Moreover, when the limit is c, it can be shown that c must be the 0 of f. Okay? Now, Newton's method does not always yield a convergent sequence. Okay? If this is your 0 here, and you happen to choose this place here where you have a first derivative of 0, it's not going to work because you're dividing by that first derivative. Now, if you choose something over here, it may work, as long as one iteration doesn't point you down to this number here and then it will get stalled out again. As long as you pick something that's going to get you past that, then it will converge, and it will converge pretty quickly. Okay? So it's a good idea to get it within the first monotonic segment, okay, that doesn't have a 0 derivative. And Terry's here. Speaking of 0 derivative. No, that's not what I was talking about. Okay. All right. We're talking about Newton's method. We've just done a couple of examples with this. And it says one way it can fail to do so is shown here in this figure. We already talked about that. All right, we're top of page 231. This is chapter 3, Applications of Differentiation, 3.8, Newton's method. Page 231, we're getting ready to go to example 3. Oh wait, well, not quite yet. Yeah. not quite ready for that yet, because Newton's method involves division by f prime of x sub n. It is clear that the method will fail when the derivative is 0 for any x sub n in the sequence. Okay? So even if you didn't start it at 0, if you happen to hit that x sub n that gives you a 0 derivative, it's going to fail. It will stop. So when you encounter that problem, you can usually overcome it by choosing a different value for your x1. Okay? Another way Newton's method can fail is shown in the next example, and that's where example 3 comes into play. Okay. The function f of x equal x to the 1/3 is not differentiable at x equals 0, right? Take a derivative. F prime of x would be what would be its derivative? 1/3 x to the negative 2/3, which is the same as 1/3 times the cube root of x squared. And when x equals 0, x squared is 0, the cube root of 0 is 0, 3 times 0 is 0. You can't do it. Okay, you cannot do that. It does not exist, not differentiable at x equals 0. And it says, show that Newton's method fails to converge when you have x1 equal 0.1. Okay? Will someone tell me, what is the 0 for that function? Where does that function cross the x-axis? Anybody? Where is that function equal to 0? Hopefully it's pretty clear, isn't it? At x equals 0. And there, the derivative doesn't exist. So this is almost, won't quite guarantee it won't work, but it comes awfully close to guaranteeing it won't work. And we'll see why. Okay? So we'll use x sub 1 is equal to 0.1. Okay? Your x sub 2 would then be 0.1 minus f of 0.1 divided by f prime of 0.1. See, I already knew we were going to need that anyway, so it would be 0.1 minus, and if you plug in, do it on your calculator, I'm not about to do this in my head, the cube root of 0.1, and divide that by 1/3 times the cube root of 0.1 squared. However you want to do that. I'll square that for you so you don't have to. Does some crazy things, doesn't it? What do you get? Help me, somebody. Anyone got it?
Negative 0.19999.
Okay, they do 0.2. I'll just take their word for it. And that's what it gives them on the first iteration, which is not a good sign, is it? We know what the 0 is. It's 0. And we went from positive 0.1 to negative 0.2. So we got further away. Well, was that just sort of a weird happenstance? Or let's try x sub 3. It would be negative 0.2 minus the cube root. And you can't take the cube root of negative numbers, 0.2, negative 0.2, divided by 1 over 3 times the cube root of 0.04, which is 0.02 squared. I did that for you. Okay? So if you have that memory key, that's a really good thing. Whatever your answer was there, store that in memory, and then do a recall minus, what the syntax for your computer would be, the cube root of your recall divided by 1 divided by the cube root of your recall squared, and hit equal to see what you get. Anybody? Still working?
0.4.
0.4. Positive 0.4. Another really bad sign. You're getting further from the 0 that you know is there. The next one, x sub 4, without doing it, but seeing the pattern here, that's going to be negative 0.8, getting even further away. X sub 5 would be positive 1.00. You're getting further and further and further away. And here's, well, they're going to show you why. I won't have to do it, okay? So we have problems, Houston, and here's why, okay? So erase the ink there. Here's what you get. Because the first derivative is equal to 1/3 x to the minus 2/3, just like you did. The derivative formula is x to the n plus 1 is equal to x to the n minus f of x to the n divided by f prime of x to the n, x sub n. And that would be x sub n minus x to the n squared divided by 1/3 of x to the minus 2/3, x sub n to the minus 2/3, which is not to me the easy. Okay, now, they just did the math here, okay, to see what this came up with, because here you happen to have a same base division of different exponents, so subtract your exponent. That would be x, you got the 3 in the denominator, well no, the 3 is in the denominator of the denominator, so it flips over and becomes 3 times x to the n. Okay, that one's not going to converge, folks. We could have just saved ourselves a lot of effort here if we had just done that. Okay? And that keeps dragging you further and further. You're going back and forth across your 0, but getting further and further from it. So if you put in 0.1 here, the next one would be 0.1 minus 0.3, which is negative 0.2. Negative 0.2 minus, which would be a plus 0.6. That would be a 0.4. That's why it keeps going back and forth the way it did. Okay? And the reason for that is, so that's negative 2x of n. And guess what? That's not going to converge. It gets further and further and further away. Okay? And that's what it produces. You don't have to go through all that if they had done all the work in between. And like I said, there's negative 0.2, 0.4, negative 0.8, positive 1.6. I did it wrong. I said 1.0, 1.6. Next one would be negative 3.2. It gets worse and worse and worse. And here's why. Okay? That non-existing derivative there, that vertical tangent line, that screws everything up. Whatever you choose here throws you way back here, further away. You choose this one, that gets you even further away here. This one further away there, that one further away there. Because your tangent lines are not converging on anything, they're getting further and further away. So this one will not work. I think we can safely say anytime you have a vertical tangent line at your zero, give it up. Newton's method will not work. Okay? The only one that will work if you happen to choose zero. Then it says, yep, you got it. I mean, it actually doesn't say that because you can't divide by zero. But, well, actually you're trying to divide by infinity, which is, that gives you a zero, so it says you're there. Okay. So anything else gets you further and further from the truth. So, two things to avoid. Avoid horizontal tangent lines where the first derivative is zero, and avoid where the first derivative doesn't exist. Same things we did for our critical values, except there you were looking for them. Now we find for Newton's method, those are what you avoid. Stay away from them. Okay, so there's example 3. All right. Now, it can be shown, this is the top of page 232, can be shown that a condition sufficient to produce convergence of Newton's method to a zero of f is that, rather bizarre, the absolute value of your function at some given value times the second derivative of the function at that value divided by the first derivative squared. If that thing's less than 1, you're okay. You're going to converge, okay, on an open interval containing a 0, okay? So if those are true with that. Now, you have to know the open interval contains a 0, but if you are, if you can get this to work, absolute value of that being less than 1, yeah, that's going to come down. Obviously, a first derivative of 0 will blow this up. That's not going to be less than 1 then, okay? Second derivative of that, trying to think what it is when you have a vertical tangent line. There is a second derivative wouldn't exist there, so that also, I think, would blow it up. So this will keep you from having first derivative of 0, that will keep you from having the second derivative of 0. I believe. I think that will be sufficient for that. Anytime that ratio then would be less than 1, you're all right. Absolute value of that. All right. You have learned several techniques for finding zeros of functions. The zeros of some functions such as f of x equal x cubed minus 2x squared minus x plus 2 can be found by simple algebraic techniques such as factoring. Factoring by grouping. That will work in this case because you see you have a factor of, when you pull out the x squared, you have an x minus 2. Pull up the minus sign, you have an x minus 2. Yeah, that will work because you know that you can do that. The zeros of other functions like this one will not work for that. Cannot be found by elementary algebraic methods. So then you'll need to do something like Newton's method. Okay. That particular function, the one I just said, only has one real zero. By using more advanced algebraic techniques, you can determine the zero to be that thing. Okay. Because the exact solution is written in terms of square roots and cube roots, it is called a solution by radicals. Okay? Actually, the book did something that this got into something else first. Let me back up just a minute to this one. The book gave you this example, the one that we did, remember? The function was f prime, or f of x, is equal to x squared minus 2. We know what that is, 1.414, blah, 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 okay? Now, let's see, and goodness gracious, 10 o'clock scholar, all right. Ryan's here, okay. All right. Anyone else come in since the call the roll? Okay. Now, to do this, f prime of x is equal to 2x. We already did this. What we didn't do before was f double prime of x is equal to 2. Okay? Now, do you remember what we used as a 0 as our first step on this one? Believe it was 1. Okay? If we plug in a 1 here and do the absolute value of f of 1 was a minus 1 times 2 divided by, when you put a 1 in there, you get a 2, and 2 squared would be 4. And this would be 1/2, which is less than 1. Okay? And it worked for us, if you remember. If you plugged a 0 in here, remember that one didn't work. I pointed that out to you, it wouldn't work. Then that would be the absolute value of minus 2 times 0. Well, wait a minute. I'm sorry. 2 times 2. But then you divide it by 0 squared. Ding, ding, ding. That will not work. Okay? And we saw that it wouldn't work. Now, they use one in the book. Say that again. They went on and did some other things with this. They used the actual numbers here. They did f of x, which is x squared minus 2 times 2, that is your second derivative, and divide by 2x squared. This would give you 2x squared minus 4 over 2x squared, and that would be 1 minus 2 over x squared. Well, that's always going to converge, okay? And that's always going to be less than 1, the absolute value of that, because 2 over x squared is going to be 1. And the closer you are, of course 0 won't work, but 1 works. Doesn't look right. Okay. Oh, it's supposed to be a 1/2. Oh, yeah, you're right. 4x squared. Sorry about that. So if you did the this will be 1/2 over 1. 1 over x squared. And that's always going to converge, because 1 over x squared, whatever it is, it's going to be a positive number. So when you subtract it from 1/2, it's going to be less than. So yeah, that always works. Whereas the other one that we did, f of x equal x to the 1/3, f prime of x was equal to 1/3 x to the minus 2/3, and f double prime of x is equal to, you tell me. What's the second derivative? Not that hard. Is it? Help me, somebody. Negative 2/9 x to the negative 5/3, exactly. Okay, now if you do this absolute value here, that would be f of x would be x to the 1/3 times the second derivative, a minus 2/9 x to the minus 5/3, divided by square the first derivative, that would be a 1/9 x to the minus 4/3. Okay? Now that's going to take some manipulation here. The numerator is going to be a minus 2/9 x to the minus 2/3. And the denominator is going to be a 1/9 x to the minus 4/3. Okay? Say again. And when you do that, you'll get a minus, or it doesn't matter about the sign, you're going to do a derivative. It's going to be a absolute value, 2 times x to the 2/3. Okay, you're doing this. F of x times f double prime. So here's your f of x, here's your second derivative of f double prime, divided by the first derivative squared. So that's your 1/9 x to the minus 4/3.
What is that?
I'm sorry?
What is that showing?
Can't hear.
Like the formula you just used?
Okay, this guarantees that you're going to have a convergent with Newton's method, if this is true. Okay? You can't give me an x, I don't think, that will make that true here, because
You can't use 0?
yeah, if you use 0, you get it, because that is the 0. That is the 0 for the function. Okay? But anything else, I think you're going to come up with something greater than 1. So it doesn't work. Let's see if I did it right. And actually, they say we should get the same answer. I'm not sure I did. Oh, I'm sorry. I misdone. This is a 4/3 here. 1/3 minus 5/3 is minus 4/3. So these go away completely. That's going to give you 2. You'll never get it, because 2 is never less than 1. Okay, I did an error in my exponents here. That's a negative 4/3 in the numerator, negative 4/3 in the denominator. They go away, and that gives you a 2. Now, that's never going to give you 1. Okay. And then once you've done that, you can go back to do this. Now, why they throw this in, I don't know. They don't do anything with it except do it. They do mention a couple of characters here, and I do say characters. I think pretty dorky looking pictures here. Niels or Niels Heinrich Abel and Évariste Galois. They were two really brilliant mathematicians. And I know Galois was French. I don't know, I think Abel may have been Dutch. I don't know that for sure. The sad part is if you look at the years of their lives. Abel, 27 when he died. Galois, 21 when he died. Okay? Both died awfully young. Now it seems like I remember reading or something or another about Abel that he got sick and died. I mean, it was a disease or something like that. Galois, if I'm not mistaken, was messing around with another man's wife and got challenged to a duel and he lost. Big time. I mean, he got killed in the duel. So that was completely unnecessary. Norwegian. Abel was Norwegian. Galois was French. Okay? And they... it was, the question determining the solution of some of these formulas, quadratic formula, things like that. In the 16th century, Italian mathematician Jerome Cardin published the method for finding radical solutions of cubic and quartic equations. Then for 300 years, the problem of finding quintic formula remained open. And that's what these two did. So they're talking about the radical functions there way beyond the scope of this course. Okay? So don't worry about it. But what it did give you is at least 3 names that you could choose if you're still looking for a paper topic. Any one of those 3. Jerome Cardin or Abel or Galois. All right, that finally finished 3.8. Homework exercises, do either 3 or 5. They're both at Calc Chat. 3 is at Calc View. Do any of the odds 7 through 15. They're all at Calc Chat. 9's at Calc View. Do any of the either 17 or 19. They're both at Calc Chat. Do 21. It's at Calc Chat. Do 23. It's at Calc Chat and Calc View. Do 25. It's at Calc Chat. 27's a Calc Chat. You can look into doing that if you'd like. 29 and or 31 are at Calc Chat. And then 33 or 35, they're both at Calc Chat. True, false, 37 or 39, they're both at Calc Chat. And 41 should be at Calc Chat. All right, any questions? 3.8. All right. Let's move on to 3.9. Okay. And this, by the way, folks, is the last section in Chapter 3. So that means before you leave today, pick up the 3rd test, because I do have it ready. It's run off. I've got it up here somewhere. And you have it. Which means, by the way, I really need your 2nd test in. Now, I think I've returned everybody's 1st test to them, except for somebody who wasn't here that day. I don't know if I don't think either one of them, 2 people. Law and Jasmine. But the 2nd test I can't return to you because I still have a few of those out. I think I have missing 1, 2, 3, 4, 5 maybe of those. So please get those in as soon as you can. All right. Chapter 3, still application of differentiation. 3.9 is going to talk about differentials. Anyone know the difference between a derivative and a differential? There's not much, okay? It's just basically how you write it, okay? So we'll hopefully understand the concept of a tangent line approximation, which is a weird, to me, a weird way to start, but that's how they start. We'll compare the value of the differential dy with the actual change in y, which is a delta y. We'll estimate the propagated error using a differential, and then we'll find the differential of a function using differentiation formulas. Okay, so they are closely tied together. So let's start with a tangent line approximation. Consider a function that is f that is differentiable at c. We know it has a derivative at c. Then the equation for the tangent line at that point c would be, well, we know the value c, x of 0. We know the y value, y, let's call it 1, x1 and y1. And we know the slope. If it's indifferentiable, find the slope. So then by the point slope formula, you have y minus y1 is equal to f prime at c, which is your derivative, that's the slope at c, times x minus c. Okay? Now, all you have to do is add the f of c to both sides of the equation, and then you have y is equal to f of c plus f prime of c times x minus c. Okay? Fine. For that point, x equals c, that is the slope of that is the tangent line. Now, that's the tangent line approximation. That gives you, if you plug in some other value for x, not c, of course, if x is equal to c, then this goes to 0, that's 0, and y is equal to f of c. We know that. But if any x not c, but fairly close to c, this is going to get you pretty close to what your y was going to be. This is called the tangent line approximation, or the linear approximation for a function f at c. Because c is a constant, y is a linear function of x. Because all these are constants here. X is the variable. Okay? Moreover, by restricting the values of x to those sufficiently close to c, the values of y can be used as approximations to any desired degree of accuracy of the values of the function of f. In other words, as x approaches c, the limit of y is f of c. Well, of course it is. That's the value at c. When x is c, is y is f of c. So this seems a little crazy. So here it is. Find the tangent line approximation for this function. F of x is equal to 1 plus sine of x at the point 1, 0. Now before we go any further, I always like to check and make sure this point is on that function. Is it? When x is equal to 0, what's sine x? Help me somebody. Sine of 0 is? 0. And 1 plus 0 is 1. So sure enough, 0, 1 is on that, is a point on that curve. Okay? Then it says, then use a table to compare the y values of the linear function with those of f of x on an open interval containing x equals 0. Okay, we'll get to that later. Let's do it first. Find the tangent line approximation. What did we just learn the tangent line approximation would be? Let me get my pen set up again. It was y is equal to f of c plus f prime of c x minus c. Okay? Now that's the linear approximation, or the tangent line approximation for the y values here. This is your actual f of x. This is your approximate f of x, which is y. Now we know that f of c is equal to 1. F prime of c we haven't determined yet, but we'll do that. And c is equal to 0, right? This is c f of c. Okay, so f of c is 1 and c is 0. Let's figure out what f prime of c is. F prime of x is equal to cosine of x, right? Okay, and when x is equal to 0, so f prime of 0 is equal to cosine of 0. Sine of 0 is 0. 1. Okay, 1. So this now is 1. At 0, at c, that is 1. So here's your linear approximation. Y is equal to 1 plus x. That's it. Okay? Now, it says use a table to compare the y values of the linear function with those of f of x on some open interval containing x. Well, let me give you a hint. Don't get an x greater than, say, pi halves, okay? You're going to be way off by that. Keep it something pretty close, okay? Like 0.1 or something like that. Let's see what they use. They use 0.5, 0.1, and 0.01, okay? So let's watch what they do. Let's just use those. 0.5. Now 0.5 is going to be a stretch. It's not going to be a great approximation. F of 0.5 is going to be 1 plus sine of 0.5. Now if you're going to do that on your calculator, what mode did you better be in? Radian mode. Don't ever get in degree mode to do this kind of stuff. Okay? And over here, I can do this one in my head. Y is equal to 1 plus 0.5 with 1.5. What is it if you plug it into your calculator? 1 plus sine of 0.5. Not that hard, is it? One plus sine of 0.5. Say again? Sine of 0.5. Don't do the inverse sine or something like that. What you got?
1.479.
1.479. You know, we're not too far off, are we? Okay? That's a pretty good. We're within 0.021. 21. That's pretty close. If you do f of 0.1, 1 plus sine of 0.1, I can do this one. That'd be y is equal to 1.1. Okay? What's 1 plus sine of 0.1? Zero, 9, what? 9. Second, 6. 8. Okay. I'd say that's pretty close. Okay. There you're within 0.0002. Okay. That's pretty good. How about f of 0.01? That's the 1 plus sine of 0.01, and this will be y is equal to 1.01. Okay, 1.01. 9 sine 9. Yeah, that's awfully close. Okay, so you see your linear approximation is not too bad as long as you're fairly close to the original. Okay, and I pointed this out to you before, I think. Let's see what they do. Oops. Let me erase what I've got. They did just like we did. They took a derivative and found it to be cosine x. And the equation for the tangent line to the graph at that point is y is equal to f of 0 plus exactly what we said before. And that's 1 plus 1 times x minus 0, so that's just going to be 1 plus x, exactly like what we said. And when you plug those in, we didn't do the minuses, but they come up almost the same. This will be minus 0.05. This will be 1 minus 0.05, which is 0.05. This came out to be 5.521. So off by 0.021. Here it would be off by very close, 0.002. And this is 0.000000002. Okay, so that's incredibly close. And same thing, we did these on this side and saw how close they were. Okay, 0.5 would be 0.021, 0.0002, and 0.000002. Okay, so awfully close. Now, there's a reason for that. I think I pointed out to you before that the sine function near 0, the slope is 1, right? And that's what we found it to be. So anywhere close here, within here to here, you're going to be almost right on the line, because that slope is almost the identity function. The sine function is almost the identity function, very close to your 0. Okay, x equals 0. So anywhere between here and here, you're going to have incredibly close results. Pi force is about -3/4. So we were within that everywhere of all the ones that we chose. All right. Now, I know there was a reason to do that, and they're going to lead to differentials that way. To me, this is not how I would go to differentials, but it's how they choose to, and it's fine. When the tangent line to the graph of f at the point CF of C, there's the tangent line, okay? What we just did, y is equal to f of C plus f prime of C times x minus C, is used in approximation of a graph of f. The quantity x minus C is called the change in x, called delta x, okay? The change in x. You were at C and you changed a little bit, delta x, okay? Now, with that little bit of change from C to x plus delta C, that's your delta x there, okay? Your y changed from here to here. That's your actual delta y, okay? Your f prime delta x, this part, the tangent line approximation was that amount. And that's what they call the dy. And I'll leave it alone like that. That is used as an approximation of the graph of f. The quantity x minus is called the change of x. It's shown here. Now, just while we've got the figure here, this is the change of x, dx, delta x. This is the actual change of y, delta y. If you went from C to C plus delta x, you went to here. So that's your actual delta y here. your tangent line approximation, that change was F prime times your delta x. That's how much it changed from alpha c to here, F prime delta x. Okay. And you say, why? I mean, what difference does all this make? When the delta x is small, really, really small, the change in y, denoted by delta y, can be approximated as shown here. Okay? This delta y, the actual change of y, is your alpha c plus delta x minus alpha c, which is approximately equal to that f prime times the delta x. Okay? For such an approximation, the quantity delta x is traditionally denoted by dx here, and then the change of y is then called dy. So the expression f prime delta x, or dx, is denoted by dy, and is called the differential of y. Okay? F prime dx is called dy from this thing right here. Okay? Now, here's your definition now. Let y equal f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number, okay? The differential of y, denoted by dy, would then be dy is equal f prime of x dx, okay? Now I'm going to show you the thing that's sort of crazy about this, and it's how I would approach it really, but I'll get it. In many types of application, the differential of y can be used as an approximation to the change in y. That is, that the delta y is approximately dy, and the delta y, the actual change of y, is approximately f prime dx. Now, this is just the notation bizarreness, I guess you would say. What's another name for f prime? Isn't that dy dx? And when you say dy is equal to f prime dx, doesn't that almost look like you're canceling out the dx's and have dy is equal to dy? To me, that's how I remember a differential. I don't go through all this tangent line approximation and stuff. That to me says it, okay? That dy is equal to f prime dx. That's it's just there.
So dy dx.
Yeah. Yeah. It's just that this is an approximation. This is the actual first derivative. The dx is actually an approximation for your delta x. Okay? And if you write it dy dx is not an approximation, that's the limit is delta x is going to 0. So it's kind of like they're using two different definitions here almost, but not really. Okay. So let's do this. Let y equal x squared. Find dy when x equal 1 and dx is 0.01. Okay? Well, what you reckon we're going to do first? What would be a good first idea? Second? Anybody? What would be a first thing to do? What's a good Jesus answer? Yeah, take a derivative. I'll go y prime is equal to what? 2x. Okay? Now, to take it even further, let's do it this way. dy is equal to 2x dx. Okay? Because if you think of y prime as being dy dx is equal to 2x, then it's kind of like, it's not what you're doing, but it's kind of like you multiply both sides of the equation by dx. Right? That's what it looks like, isn't it? Okay, so let's try it. When x is equal to 1 and dx is equal to 0.01, your dy would then be 2 times x's 1 times 0.01. That's your dx. It really should be a delta x, but they're calling it your dx. Okay? So this will be your dy is equal to what? Pretty easy math. What would it be?
It's
Second? 2 times 0.2. Exactly. Okay? Now let's see what it actually is when you're doing the delta y, the actual change of y when x is equal to 1 and the delta x is 0.01. So your y then, the actual y, your new x is going to be x equal 1.01. All right. George, right? All right. We're in chapter 3, which is different application of differentiation. We're in section 3.9, the last section in the chapter, differentials, and that's what we're doing right now is example 2 on page 236, comparing the delta y with the dy. We just did our dy here. Your delta y is going to be the y2 minus y1. Let's just call it that to have some reason. Your y1 is going to be when x is equal, the y1 is going to be x1 squared, where your x1 is 1. This would be 1 squared, which is 1. Okay? Your y2 here is going to be your new x, x2 squared, and this new x, I'm going to call x2, is 1.01 squared. Someone pull out a calculator and see what 1.01 squared is. You might be able to do that in your head. Okay, because you added to your x, your delta x. That's the new value. 1 point what? Okay. So your change of y, your actual change of y, is going to be your y2, 1.0201, minus your y1, which was 1, and this is 0.0201. So here was your delta y, dy, here was your actual change of y. Awfully close. 0.0001 apart. Really, really close. Okay? And that's what your differential will do for you. It gives you a very close approximation of what your actual change will be. Okay.
in the book. Will it say d of x or will it say delta x?
Say again?
The book, will the question say d of x or delta x?
Okay. They're letting the d of x equal the delta x. Okay. The delta x, the actual change of x is 0.01, and we're going to say, well, let's call that d of x.
Okay.
And then using the d of x, we're going to come up with dy. dx will come up with dy. Then using the delta x, we'll actually come up with the actual change of y, and that will be this one.
So will they be two separate functions or will they be the same?
Okay. This is the approximation. This is the actual. Yeah. And they're close. That's what the point is. They're very, very close. Okay? All right. So let's see how they did it. I probably cut some corners here because to carry you through all their thing, if you just do it this way, the dy is really, really easy. Okay. Because the y is equal to f of x is equal to x squared. Okay. You have f prime is equal to x. First thing you do, take a derivative. The differential then would be dy is equal to f prime dx, which would be f prime at 1, that's your x value, times your dx, which is the same as your delta x, 0.01, and that gives you 0.02, just like we did. Precisely what we did. Okay? Your actual delta x, which was called your dx, the change in y would then be the change in f of x plus delta x, that's your, well, I was calling y x2, and this was calling this y2, minus x1, y1. It just was easier than writing this, but this maybe is more precise, so if you like this better, the x plus delta x would be 1 plus 0.1. So 1.01. F of x is just 1. So do this one, which is what you did, and you found that to be 1.0201 minus 1 is the difference there is 0.0201 compared to 0.202, a very good approximation. Very good. This is the actual change. There was the approximate change. Now, this figure shows what they're kind of talking about, the geometric comparison. This is your function, y is equal to x squared. Now, they've blown it up really big. You can't see that is a parabola. Somewhere down here it's going to curve around and come back up. So this is wing of a parabola, a little bit between 1 and 1.01. Okay, pretty small change here. That's almost a straight line, but not quite. Here's the tangent line. This is what your approximation is, 2x minus 1. That's your slope of your tangent line. That is the equation of the tangent line. You're plugging this in, the point this would give you your point 2. It was easier the way we did it, but you still get this. So there's your dy, the 0.02, and here was your actual change of y. F of x 1.01, that would be that value, 1.0102, and then this would have been your, 1.0201, and this would be 1.02. So your dy was 0.02, and your delta y was just a little bit more. This looks like a lot more, but on a scale that made any sense at all, these would be so close together you can hardly see them apart. They've really blown it up so you can tell the difference. This came out being 2 times 1.01 would be 2.02, minus 1 would be 1.01. That's this value here. So that change of from 1 to 1.01 was 0.02. Okay? And then this was 0.0201. So just a little bit more there. To me, the picture isn't really all that helpful, but it just shows how it makes it seem like it's a big difference, but it really, really is a very, very, very small difference on any kind of scale that makes sense. Okay. Now, something that is of perhaps more interest to maybe certain engineers like industrial engineers or probably mechanical engineers too, if you are making an approximation, how badly is your tolerance, what you're allowing to be an error, how bad is that going to bite you in the future? Okay, this is what they call error propagation. How does a little bit of an error here by using an approximated value, how does it change things? If you let x represent the measured value of the variable and x plus delta x represent the exact value, then the delta x is the error in the measurement. Okay? And guess what? You can't really measure anything that you're not going to have some error. Number one, your measuring device. It may not be precise. It may be close, awfully close. And then, how you measure it, are you measuring it correctly? Have you got a little bit of a parallax when you look at that? You know, there can be lots of places where you can have error measurement. If you're making a measurement, there's always going to be some error. Some uncertainty about what your actual value is. It's between this line and that line, but I don't know which one it's closer to. That's an error, okay? You round it off to whichever one it's closest to, you have an error, okay? Finally, if the measured value x is used to compute another value, f of x, then the difference between the f of x plus delta x and the f of x is called the propagated error, okay? Because you use this value that you rounded to here, but the actual was this, but you didn't know exactly how much difference you had there, so you've now had a propagated error, okay? And that's your delta y, okay? The difference between the y value at the actual and the y value of your measured, then that gives you your propagated error. Your measurement error was this delta x part here. Okay. So here's example 3. The measured radius of a ball bearing, and this is a stupid statement here, okay? The measured radius of a ball bearing, you don't measure the radius of a ball bearing. What they're showing here is the diameter of a ball bearing. A radius is from the center to the edge. How can you get anything to measure from the center to the edge? You can't. You measure edge to edge, which is a diameter. Okay? But they say the measured radius. This is sort of silly. They should be saying the measured diameter of a ball bearing is 1.4 inch. Okay? As shown in the figure below. If the measurement is correct to within 1.01 inch, in other words, your device and how tight you did it, whether you're smashing the ball or not, whether you're compressing it or not, is 0.01 inch. Estimate the propagated error in the volume of that ball bearing. Now, it first says estimate the propagated error. Okay? What is the volume of a sphere? Anyone know? Uh-oh. Second? Okay, that would be if it was a rectangular parallelepiped or a square. Okay? This is a sphere. Okay? If you want to look at the back of your book, or if you got a book, the back inside cover, a sphere, the volume is, and you can look it up anywhere on the internet too, 4/3 pi r cubed. The volume, now this is a capital V volume. Little v in physics is usually velocity. Capital V volume is 4/3 pi r cubed. And that's why they used r here, because the formula for the volume of a sphere using diameter is really a lot nastier looking formula. Okay? Very reasonable, but yeah. So, estimate the propagated error in the volume of the ball bearing. Well, what we're going to do is, guess what we're going to do? Take a derivative. dV dr. R is the independent variable here. What would that be?
Oh, you're talking
What would the derivative be? dv dr. Not that hard, folks.
4 pi r squared.
4 pi r squared, exactly. Okay? Now, this is mathematicians don't like it when you say this. Then dv, that is the propagated error, is equal to 4 pi r squared dr, that is your measurement error. Okay? So this will be dv is equal to 4 pi times the measured radius, 0.7 inches, times your measurement error, possible measurement error, 0.01 inch. Okay? Oops. I didn't square. Sorry. So this will be 4 pi times 0.49 square inches times 0.01 inch. Okay? Someone with a calculator tell me what that comes out to be. 0.06, and that would be cubic inches. It's pretty close, okay? Now, they don't say find the actual, okay? But if you did do it, let's do with the measured would be 4/3 pi times 0.7 cubed. Give me an answer for that. I left off the inch. But 4/3 pi times 0.7 cubed. One 1.4367, is that what you said? Okay. Now, let's do the, I'm going to call it actual. What if it was 4/3 pi times 0.71 cubed? Okay. What would that one be? 1.49 what? 499? Is that what you said? Okay. Let's subtract 1.4367 from that, and you get, I don't know if that's important there, but this would be 2, 6. This is the, no, cube. Actual difference in volume, that was your estimated difference in volume. Pretty close. Pretty close. Okay? And this was a lot easier to do, the differential. Okay? And you got a pretty reasonable approximation. Okay? Let's see how they do it. I think I could probably just forget this. Yeah. The formula for volume of a sphere is V is equal to 4/3 pi r cubed, where r is the radius of the sphere. So you could write r is equal to 0.7, and you're within 0.01, minus 0.01 or plus 0.01. Okay, we just did the plus side when I did it. Okay, to approximate the propagated error, differentiate that. dv dr is equal to 4 pi r squared, and have that be the delta V is approximately equal to dV, and that would be 4 pi r squared dr. If you just multiply the dr, that gives it to you right then, okay? And that would be, and they did the plus or minus on it, and that would be plus or minus 0.06158. Did you have that many digits? I don't know. We just said 0.06, okay? So the volume as propagated error is about 0.06 cubic inch. That's what they said too, okay? Now that ratio of that, they're getting into something different now. This is the propagated error to the actual volume, dV over V. And if this happens, the 4's go away, the pi's go away, and 2 of the r's go away, and you wind up with 3 dr over r. So 3 times 0.01 plus or minus 0.01 over 0.7, and that would be plus or minus 0.0429. Now that's called the relative error. It's the error compared to what your original measurement was, okay? That means relative error. Correspond to a percent, that would be about 4.29. Move the decimal 2 places, about 4.29 or 4.3%. Not too bad. Now, for many of you, if you are into mechanical engineering, well, just about any kind of engineering, you'll have what they call tolerances. That's how precise does the piece need to be, okay? Now, I have a younger brother who used to work for an electric motor company, and usually they had, so that was more electrical engineering. Most of the devices they had, I don't know, I'm just going to say 0.1% or something like that was the tolerance. But he said if they had to deal anything with the Navy, he said Navy specs were almost 10 times more precise than what any other specs were. Okay, so in other words, sometimes you have things that are pretty reasonable, okay? Other times they can be really, really tough to meet. And then you have to have so much better, what do they call it?
I would imagine you have to have better tools too to get that precise.
Say again?
I would imagine you have to have better tools too.
Yeah.
Precise.
Exactly. And, you know, and frankly, I was in the Navy, and you didn't want things going wrong because it's sort of hard to find parts out at sea, you know, so otherwise you have to carry double or triple everything. So it was, Navy specs were always very, very precise. And if they're given as a percent error, that's based on relative error. The actual error was what we had was 0.06, which you would have thought would be something like 6%, but no, that is relative to what your actual measurement was, and your actual measurement was 0.7, so that dropped down to the relative error. Okay. Now, that was example 3. Now we're moving to calculate differentials. Now we haven't had a break yet, and we passed when we usually take one. Does anyone need a break, or are you okay to keep going? Say something. Break or no break? What's that? I can't hear. Huh?
Don't we usually have a break at 10?
Yeah, usually at 10. I said I got carried away and missed it. Do you need a break? Let's say.
Yeah, we'll take
Let's take one. Let's keep it less than. All right. Any questions so far? Sorry, we went over a little bit. Last time I looked at my watch, it was 1:45, and I looked at it almost 10:30. So I went, whoa. So, but this is a decent break point. So let's move on to calculating differentials, as if we haven't been doing that already. And each of the differentiation rules can be written in differential forms. In fact, anything you can write as a derivative, you can write it as a differential. Okay? Let u and v be differentiable functions of x. The constant multiple, d of cu is equal to c, pull the c outside, times du. Same principle. Somewhere a difference. The differential of u plus or minus v is equal to du plus or minus the dv, the differentials. The product, same rule, d of uv, the product rule, u times dv plus v times du. There's one reason we're doing this right now. And the reason is, look at what the next chapter is going to be. Integration. Integration is going to undo differentiation, and it does it much better with differentials than it does with derivatives. I mean, it does it with derivatives too. So here's your product rule and differential. Your quotient rule in differentials, d of u divided by v is low d high, okay, v du minus u dv over low low. Okay, low d high minus high d low over low low, d squared. In fact, that's what I've been telling you. That's where the d comes from. Differential as opposed to derivative. Okay, same deal. Okay, so let's do a few. Yeah, I can do this. What's the derivative of y? If y is equal to x squared, what's its derivative? Say again? 2x. Perfect. Well, how would you write that in differential form? In derivative, you say dy dx is equal to 2x. How would you write it in differential form?
dy equals 2x dx.
Perfect. It's the same stuff. It's sort of like you're multiplying both sides by dx. That's not what you're doing, but it's like that. Okay, how about this one? What would that be? What would be the first thing you do to that one? Okay.
Is it 1/2 x?
Okay, I'd write it as x to the 1/2 and then take a derivative. And what would the derivative be? dy dx would be 1/2 x to the negative 1/2, which would be 1 over that. I wouldn't ever do it that way. I would do it the other way. And if you wrote that as a differential, what would that be? dy is equal to? 1 over 2. And then you can write the dx up there. I would have written this as x to the 1/2. I would have written this as 1/2 x to the minus 1/2. I would have written this as 1/2 x to the minus 1/2 dx. Okay? But that's perfectly fine to write it that way too. Okay? How about this one? Y is equal to 2 sine x. What's its derivative? dy dx, what would that be? Second? 2 cosine x, perfect. And then, written as differential, dy is equal to dx, perfect. It's that simple, folks. Okay? And here's why. Whoa! Y is equal to x cosine x. How would you write dy dx? What would you use? Say again? They're multiplied together. Hint? 1 times? Okay. This is, they're multiplied together. What is the answer to a multiplication problem? Product. So guess what rule you're going to use? Product rule. How does that go? Okay, say that a little louder.
fx times g of x plus.
Wait.
I'm sorry. Derivative of
Yes.
function times the second function plus derivative of the second function times the first.
Perfect. So what would that be then? What would it be then for this one? If x is your first function, cosine x is your second function, what would be the product?
It would be
X times
negative sign
negative sign. Okay, and that's what they have here, negative x sine x
plus
plus cosine x. Perfect. So what would be in differential form?
cos dy equals all that times dx.
That's it. dy is equal to that mess times dx. Exactly. Now, when I do it, I like to write the positive first, so I would have done it that way. It doesn't matter which order you do it, but I just like to lead off with the positive if I can. I don't think there's an e, is there? Yes, there is. So what would that be? Number one, I wouldn't write it that way. I would change it. How would I change it? X to the minus 1. What would be the derivative?
That's the negative exponent. That's like a negative 1.
Yeah, x to the minus 1. Yeah.
So it would be like negative 1x minus negative 2. Or negative square.
To the negative 2.
Yeah.
Okay. So that would be, I wouldn't write it like that, but they did, negative 1 over x squared. And what would that be in differential form?
Dy equals dx over x squared.
Negative dx over x squared. Don't forget the minus. Yeah. That's it. I mean, that's all there is to it. Okay? The notation in example 4 is called the Leibniz notation for derivatives and differentials, named after the German mathematician Gottfried Wilhelm Leibniz, I think is how you pronounce it. Now, if you remember, he is given credit for developing calculus independently of Isaac Newton. But frankly, that caused probably, I'm going to just make a guess, probably 40 to 50 years of intense dispute on not furthering calculus, but on arguing who invented it. I think everybody concludes that Newton came up with the idea first. Okay? Now, the question is, when Newton was coming up with this idea, he ran it past several people, including Leibniz. Leibniz was a very well-known, well-respected mathematician in Germany. And Newton ran it past him and several other good mathematicians to get their feedback. Well, Leibniz, a few years later, published before Newton did. Newton was a stickler for details, and he didn't want to publish unless he was absolutely sure no one could question him. He had an insecurity that way. Leibniz didn't care, okay? And he published, and Newton claimed from then on that Leibniz used what he had sent him to get it out there first. So many people, especially in continental Europe, considered Leibniz the developer of calculus, and of course the British went with Newton, and they argued and fought about it for the rest of their lives. I think Leibniz died first, even though he was younger. But it was a terrible waste of mind power for them to be fussing over that the rest of their lives, but they did. But anyway, the unique things about Leibniz, he used a much nicer notation than Newton did. Newton did something that he understood was very practical, meant whatever it meant to him. Leibniz used a different notation. That's the main reason he's given credit for anything, is he came up with a better notation. Okay. But anyway, this came after him. There's another potential paper topic, or 2 or 3. Okay. Differentials can be used to approximate function values. To do this, for the function given by y is equal to f of x, use the formula. Does this look familiar? F of x plus delta x is approximately equal to f of x plus your dy, where your dy was f prime dx. Okay? Which is almost exactly what we did in our tangent line approximation. That's derived from the approximation delta y is equal to f of x plus delta x minus f of x, which is approximately equal to dy. The key for using the formula is to choose a value for x that makes the calculations easy. Okay? That's the key. Okay? Choose the x that makes it easy. So let's do this one. Use differentials to approximate the square root of 16.5. Okay? Say again? So what we're saying is, looking back at before, what we're going to do is the f of x plus delta x is going to be about f of x plus your dy, okay? And the dy being f prime dx, okay? So, our function here is the square root function, right? Agreed? Okay. And your actual value is the square root of 16.5. We're going to say that's is exactly equal to the square root of 16 plus 0.5. Okay? That is exactly that. Okay? That's approximately equal to f of x plus dy, which would be your f of x would be the square root of 16 plus the square root of 0.5. That's the approximation. This isn't exact, but it's approximate. Okay? And what is your dy? Your if your f of x is equal to the square root of 16.5, then it's the your dy is your f prime dx, okay? If this is your, what we're calling your dy then, okay, and that's not exact, but it's going to be close to it, then what you have this to be is f prime dx. With the dx is your 0.5. That's the delta x or your dx, whichever you want to call it. So if this is your squaring function, okay, if your f of x is equal to, I'm going to write it x to the 1/2, what is your df? Didn't we just do those? I even wrote it in the easier form for you. It's what? 1/2 x to the minus 1/2. And then write your dx there, okay? So this is your df, or your change of y, okay, is equal to 1/2. And remember, the x we're using here is 16. So this is 1 over the square root of 16 times your dx, and your dx was your 0.5. Okay, so it would be 1/2 of 1/4 times 0.5. So this would be half of 1/8 is 1/16. Okay, I'm doing the math fairly quickly there. Hopefully it's not too bad. So that is your dy. So this would be 4 plus 1/16. And 1/16 is 4.0625. Is that right? I can't remember for sure. Okay. A quarter is 0.25, an eighth would be 0.125, and this would be 0.0625. Okay? Now, this is what our approximate thing is. Okay? The differential. This is our using differentials. Someone plug in and see what the square root of 16.5 is. .0620. I'd say that's pretty close. Okay? You had to use a calculator to get this one. We did this one strictly in our heads. It's the square root of 16 plus the dy here. And the dy is f prime dx, where the f is x to the 1/2, the square root of f. Okay? But we're using it 16 with our dx being the 0.5. Okay? So that would be 1/2 of 1 over the square root of 16 times 0.5, and that's 1/2 times 1/4 times 0.5, which is 1/16. 4 plus 1/16 is this. Pretty close. I would say close enough for government work. Okay? That's going to give it pretty closely. So, in one sense, they can really ease your, oh, I just realized we skipped example 5 and 6. We went straight to example 7. We'll come back and do example 7. Let's go back and do example 5 and 6. Wait, that's not what I want to do. Okay. All right, let's do example 5 first. Sorry, I jumped ahead, didn't mean to. Here we have y is equal to f of x is equal to sine of 3x. Okay. What we're doing is finding the differential of a composite function, which hopefully you'll see is pretty straightforward. How would you do this to find its differential? Wouldn't you first? Derivative. dy dx is equal to cosine 3x times 3. Okay? So then your dy would be 3 cosine 3x dx. Yeah, that's it. Okay. What's that?
The last one was like that.
I can't hear.
The last one we did was like that.
It was similar, yeah, but we didn't have a composite function with it, did we? No. Yeah, not quite. But yeah, very similar. Okay? That's the only difference here. Here's another one. Y is equal to f of x is equal to x squared plus 1 to the 1/2 power. How would you get its differential? dy dx equal to 1/2 x squared plus 1 to the negative 1/2 times 2x. I put it in there to make it easier to deal with. The 2's go out, so you have x over x squared plus 1 to the 1/2 power. Okay, so write that in differential form. It's easy, this is easy stuff. dy is equal to this, x over x squared plus 1 to the 1/2, or you could write that as a square root, and then you could write the dx up here, you could write the dx off to the side, you could write it wherever you wanted to over there. Okay, and yeah, they wrote it off to the side. It's fine. They put it under the square root. That's fine. Both of those are fine. All right, and then we got to do this problem. So let me clear my screen. We'll go back and do example 7 now. Okay. All right. Now, using f of x equal the square root of x. That's obviously your squaring function. F of x equals square root of x, square root function. So f of x plus delta x is f of x plus f prime delta x. That is what we got from here. They find weird ways to do it. This thing that we're looking for is f plus f prime delta x. Okay? So jumping right to the chase there, you get f plus f prime delta x. Well, the f of x is the square root of x. Okay? Plus, and the derivative of the square root of x is 1/2 x to the minus 1/2 times the dx. Okay? So this is square root of x plus, and then writing that with square root form, you get this. And then, here's where the magic happens. What they said is use you're looking for this thing, which is the square root of that. Okay? Let's just use an x that's easy to evaluate that square root of, and let's take that to 16. Okay? Plus, and then we'll have the rest of this in here. That would make your x 16, your dx 0.5. And then your f of x plus dx, which is the square root of 16.5, is equal to the square root of 16, that's this part, plus 1 over 2 times the square root of 16 times your dx, which is 0.5. And that's what I did in a slightly different way, and that gives you 4 plus 1/8. 1/2 of 1/4 is 1/8 times 0.5 is 1/2. I have so many 1/2s in there in different forms, and that would be 16, so it's 4.0625. Now, when you actually do it, so this is approximately that, and when you actually do the calculation for the square root of 16.5, oh, they didn't do it. Okay. We did, but they didn't. That's their approximation to it using differentials. Okay. They just left it there. All right. Now, no, this is the same. So the tangent line approximation to f of x equals square root of x at x equals 16 is this approximation. G of x is equal to 1/8 of x plus 2. Oh, that's a tangent line approximation, which to me, why bring that back up here, but they do. Okay, now how did they get that? Your derivative was, remember, 1 over 2 times, and the 2 is times square root of 16, so that's where your 1/8 came from, times your x, and then the plus 2 they got from the slope-intercept form. They skipped a bunch of steps here to get to this form. For x values near 16, and 16.5 is awfully close to 16, that would be just up here a little ways, and that shows why this approximation is so good, because the blue line, you can see it finally starts deviating here, and just beginning to see it deviating there. The 16.25 is right there. That's going to be an awfully, awfully close approximation, okay? And that's what they're doing there. Skipping a lot of steps to get there, but why even go back to the tangent line? I don't know. I guess it's showing you how close it is, okay? And is that the last? Yes, it is. That is the last example in this section. Homework exercises here. Do any of the odds 5 through 9, they're all at Calc Chat. 7's at Calc View. Do 11 is at Calc Chat. Do any of the odds 13 to 17, they're all at Calc Chat. 13's at Calc View. Do any of the odds 19 to 27, they're all at Calc Chat. 23's at Calc View. Do 29, it's at Calc Chat. 31's at Calc Chat. And then you choose any of the odds 33 through 41. A whole bunch there. You might want to choose more than one, but those are all at Calc Chat. Then either 43 or 45, they're both at Calc Chat. 43 is at Calc View. You can explore doing 47, is at Calc Chat. There's a couple of true false, 3 of them in fact, 49 to 53. You could do any of those. Those are at Calc Chat, and that's it. Now, if you need more exercises, these are all at Calc Chat. None of these are at Calc View, but any of the odds 1 through 7 on your review exercises, they're all at Calc Chat. Now, I think in the back of the book they have all the answers for the evens and odds, but they only at Calc Chat have the odds. So 1 through 7, 9 or 11, 13 through 17, 19, 23 to 25, 27 to 33, 35, 37 to 41, 43 to 47, 49, you can think about doing that one anyway. 51's a writing problem, so you can think about that if you'd like to. Modeling data is 53. Then any of the odds 51 to 63, 65 or 67. Any of the odds 69 to 77. Some applied problems 79 through 87. Now some of those, wait. Some of those are your, that group I just did was the optimization problem. So you don't have to do those unless you think it's going to be something you would use in the future, okay? But then picking up with Newton's method is 89 or 91, 93, 95, 97, and 99 or 101. 99 and 101. There's a little thing on problem solving. If you're interested in that, you certainly can do that as well. So we're ready now for chapter 4, which is integration. All right. A couple of things about this before we move on. Let me go on and give you, and I had it here on top, and now I can't find them. Okay. Here is your test 3. Okay. Chapter 3 test. You'll keep on in test 2. Keep on in test 3. Okay. And you'll keep on in test 2. I want to make sure I remember to give you those. Now, technically, they're due a week from today. You can have more time than that. But, folks, if you haven't gotten in, I think I'm preaching to the choir here pretty much. If you haven't gotten in your test 2, please get that in, because now you got test 3 on top of it. So let's not get too far banked here. Okay. Now, a couple things about chapter, well, let's see. Get on to chapter 4. All right. It'll come up here in a few years. Here it comes. All right. Now, chapter 4 is going to be talking about integration. Now, this is typically where you end Calculus 1, okay? Except for the fact that this book has not gotten you into what they call the transcendental functions, the early transcendental functions. So what we're going to do is chapter 4, which is integration, and then we're going to go to chapter 5, which is going to do some of your early transcendental functions, and it's going to do differentiation and integration. So it's really put together rather poorly, and that's why beginning in the fall, we're going to another calculus text by these same authors, but it's going to incorporate the transcendental functions within. So we wouldn't have this chapter 5 that's separate, going back and reinventing the wheel. So chapter 4 is a relatively short chapter compared to the ones we've been doing. Chapter 3 was 9 sections, okay? Oh, and by the way, I meant to say this too. Let me see if I can do this quickly for you. Mark my place here so I don't lose it. On your test, the first 2 questions are from section 3.1, I believe. Okay. The third question is from 3.2. Third and fourth questions are 3.2. The fifth question is 3.3. And fifth and sixth questions are 3.3. The seventh is 3.4. The eighth one is 3.6 because we sort of skipped 3.5, okay? And then the ninth question is 3.8 because we skipped 3.7. And the 10th question is the one we just did in 3.9. So 1 and 2 are from 3.1, 3 and 4 are from 3.2, 5 and 6 are from 3.3, 7 is from 3.4, 8 is from 3.6, 9 is 3.8, and 10 is from 3.9. Okay, now notice and I didn't provide graph paper. Do all of you have graph paper? Or do you want me to get you? Okay. I forgot to run any off. I can have that run off and bring it in on Wednesday. Is that okay? Okay. So I'll try to do that. Because number 8, you got to sketch the graph, but you also have to analyze it. Now, what do we mean by analyzing? What 4 things do we look for? Pre-calculus things.
Domain and range.
Say again?
The domain and range.
Okay, actually 6 things then. Domain, range,
X and Y intercepts.
X and Y intercepts, vertical and horizontal asymptotes. Those are part of analyzing the function. Now, not all functions will have all those things that you can do with, but most of them you will have something to say about each one. Either none of them or don't exist or something like that. Okay? Then comes the calculus part. What do you do on the calculus part? What do you do in calculus? First and second derivatives. First derivative tells you increasing, decreasing, and critical values. Second derivative tells you concavity and points of inflection. So when it says analyze the graph, you're going to have to sketch it, but where you sketch it, if you got graph paper or whatever, you've got to list those things too. So domain, range, x and y intercepts, vertical, horizontal asymptotes. I need to see your first derivative, where it's equal to 0, where it doesn't exist. Those are your critical values. You don't have to put increasing, decreasing, but it's not a bad idea to do that as well. You can show it on the graph. Okay, and then second derivative, where it's either 0 or doesn't exist. Those could be your points of inflection, and therefore concave up where and concave down where. Okay, so that's what we mean by analyzing the graphs and sketching the graph. So wanted to make sure you understood all that needs to be done for that one there. And it's not done on this. I mean, if you want to do it on the back of the page, you can. Graph paper is probably going to be your better bet. And if you don't have it, I'll try to get your graph paper by next time. Okay? I forgot to run those off. All right. Is there a question or just? Test 2, yes. I said that earlier, too. All of Test 2 has been great. Now, I don't have it on Blackboard yet, but I'm going to try to get it there this week if possible. But if you want to see it after class, you can certainly come up and see after class. Now, I can't return them to you because not everybody's turned them in yet. So please get those in. All right. Let's get back to integration, chapter 4. Say again? We got plenty of time. Is that what you're asking? Okay. All right. I thought that's what it was. Okay. Integration. We're going to start by not even calling integration. We're going to call it antiderivatives. Okay? And that leads to what we call indefinite integration. Okay? Now, if you think about it, after you probably learned to count, what was the first operation you did way back in preschool, kindergarten, first grade, somewhere back there? What's the first operation you did? Addition. Okay? And then shortly after that, once you finally memorized all those flashcards or whatever you did back then when you did it, and you thought, hey, I've almost got this tied up in a knot, then they turned around and had you undo it with subtraction. Well, finally, when you got that settled, you say, okay, I almost have this done yet. Then they introduced multiplication. Then you undid multiplication using division. And sometime many years later, probably, you did raising things to powers. Okay? And then after that, you undid that by taking roots. Right? That undid that. So everything we've done in math has been doing something and undoing it, doing it and undoing it. We just done differentiation. Guess what we're going to do now? Antiderivatives. Rather than taking derivatives, we're going to do it backwards. Antiderivatives. So our overview is write the general solution for a differential equation. I hate it that they jump right into differential equations and use definite integration, integral notation for antiderivatives, indefinite integration. We'll use basic integration rules to define the antiderivatives, and we'll find a particular solution for a differential equation. Okay? Jumping into differential equations. So let's start with antiderivatives. Now, here they're going to start using a notation, and they're going to use it fairly uniformly for a while, and after a while they start mixing it up a little bit. But what they're going to do now is find the function capital F, which is going to be one whose derivative is this little f. See, before we always started with a function and said, now what's its derivative? We started with a little f and said, what's its derivative? And called it f prime. Now we're going to start with a function. We say, this is the derivative. What is the capital F that this is the derivative for. Probably most of you can look at this and see what you guess. What capital F would that be? Whose derivative is 3x squared. Say again? What capital F could you have whose derivative is 3x squared?
I guess it would be
X cubed, exactly, x cubed. You might use your knowledge of derivatives to conclude that if your capital F was x cubed, your d by dx of x cubed, which would be your little f in this case, would be 3x squared. What you've just done is find the function f, which is the antiderivative of that. What function did you have to start with whose derivative is that? Like subtraction and addition, that kind of stuff. So here's the definition of an antiderivative. A function capital F is an antiderivative of little f on an interval I where capital F prime is your little f for all the x's in that interval I. Okay? So now we've got to think backwards. You're undoing what we were doing in the last two chapters. Note that f is called the antiderivative of f rather than the antiderivative of. Okay. Here's the key. It's the article is called an antiderivative of f rather than the antiderivative of f. And here's why. What if your f was x cubed? What's its derivative? 3x squared. What if your f was, capital F was x cubed minus 5? What's its antiderivative? What's its derivative? 3x squared. What if it was x cubed plus 97? What's its derivative? 3x squared. So you see it's not the only antiderivative, it's just one of many antiderivatives. Because all of these are derivatives, the derivatives are 3x squared. So what you do to make it general, for any constant capital C, the function f of x equal x cubed plus c is an antiderivative of f. If all you do is add the c to it, then that makes it general. Okay? Now, why this book uses a capital C, I don't know. Sometimes I'll just put little c because that's how I'm used to doing it, but either one, it doesn't matter. It's just a constant, okay? So here's how we represent antiderivatives. If f is an antiderivative of little f, capital F is an antiderivative of little f, on an interval I, then g is an antiderivative of f on the same interval I, if and only if g is of the form g of x is equal to sum f of x, capital F of x, plus c, for all the x's on that interval, where c is a constant. So in other words, if you have an antiderivative, add a constant to it, it's still an antiderivative. Okay? Adding a constant doesn't change it. Okay. Using that theorem, we can represent the entire family of antiderivative functions by adding a constant to the known antiderivative. For example, if you know that d by dx, that's what this d sub x stands for, of x squared is 2x, you can represent the family of antiderivatives of f of x equal 2x by any g of x equal x squared plus c. So when you do the antiderivative, you get x squared, add a c to it, and you've got the whole family of antiderivatives of f of x equal 2x. Where c is a constant, and constant c is called the constant of integration. Now that will come into large importance in physics. You use those quite a bit. Okay, how are we doing on time? What's that? How much?
Yeah.
I can't hear.
It's about that time.
I know it's about that time. How close to that time?
Like 2 minutes.
How much? 2 minutes? Okay. I hate to stop right in the middle of this. Let's get this slide. The family of functions represented by capital G is the general antiderivative of f, and that capital G is x squared plus c. General solution for this differential equation g prime of x equal to x, or your little f of x, your little g of x. The differential equation in x and y is an equation that involves x, y, and the derivatives of y. Why they introduce this now, I don't know. For instance, y prime is equal to 3x. Sorry. Y prime is equal to x squared plus 1 are examples of differential equation. You have the derivative on one side and some function of x. Could be a y, but usually just x is on the other side. Okay. We'll start next time with example 1. Okay. Yeah. Okay. Any questions? All right. Everybody got a copy of your test. They're due, get started on them so you'll know if you have questions by next time. And then technically due on the Monday of next week, but you have more time if you need it. Just get them to me before we get through with chapter 4. And chapter 4 is a short chapter, okay? So we're going, but it's got long sections, so it'll take us a little while to get through it. Good deal. Any questions?
I would like to see the second test.
What's that?
The second test.
Oh, you want to see it? Okay.
This is my second.
Okay. Good deal. Thank you. All right. Okay. Now, let me